it's in the complex four-dimensional setting. It's the idea of taking Donaldson invariants and trying to get kind of deformation invariant holomorphic version of that. And this is a rather technical result that just proves that in a non-compact setting these make sense. So before I move on to the actual talk, I'm gonna just kind of mention the fact that there's a lot of different parts of geometry that go into the proof, but one should never really worry about, apart from kind of some technical details about what these geometries are. So the question of orientation is very topological, and even if one works over higher stacks or stacks and in schemes which sit in each other, these categories, and one also has to use the notion of topological stacks or even C-infinity stacks and manifolds. All of this kind of boils down to their topological information because one has functors from all of these categories into the category of topological spaces. So why I'm saying this is that so that you don't really think about all the horrible moduli spaces or the objects that I talk about in any other way than kind of as geometric objects, which in the end give something topological. So let me begin now with the actual talk. So what I'm thinking about, well, I'm going to start first with a projective Calabi-Yau fourfold, meaning that this is X is a projective variety and omega is an algebraic nowhere vanishing holomorphic volume form, or a section of the canonical bundle. For a holomorphic vector bundle, one has the usual duality, which on Calabi-Yau fourfold has an extra form, so to call it the hash, and it's a duality on the Delbois resolution of the endomorphism vector bundle of E, which is given by composing the Hodge star with the inverse of the holomorphic volume form. So it only kind of looks, it really is just the duality on the Delbois resolution. And using this notation, so these are called X groups, which are the homology groups of the resolution. One gets the duality on the X groups. In particular, one obtains that the second X group, if you just plug in I is equal to 2 here, you get that it's self-dual. In particular, you get a bilinear form this. And this whole idea, in fact, works very much in static on perfect complexes also, where a perfect complex is a sequence of vector bundles, essentially. It's not given uniquely in such a way, but one should really think of it as a sequence of holomorphic vector bundles. And one gets again the duality, which is called a Serre duality in that setting.
Sorry, what's A? What's A? A0I?
So that's the anti-holomorphic part of, so the anti-holomorphic part of so these are basically the 0p forms, okay, on your Calabi-Yau. And now, what is this all about? Why am I talking about this duality? It's because if one takes alpha, which is an element of cohomology sitting in the even degrees, then one can take moduli space of sigma stable coherent sheaves, where sigma is some stability condition, with a given Chern character alpha, and these moduli space, one would like to kind of count the number of these stable sheaves inside of this moduli space. And for that, Cao conjectured in 2015, an existence of some virtual fundamental class which relied exactly on this existence of duality. And it was then constructed later by Borisov-Joyce using some very technical derived algebraic and differential geometric, so it's derived differential geometric arguments. And later on, so this hasn't come out yet, this is just a draft for now, but Richard Thomas and his postdoc O have been working on expressing this virtual fundamental class in terms of some algebraic geometric arguments using isotropic cones, but it still relies on some derived algebraic results from Joyce et al. So the point is that the existence of this virtual fundamental class is very much dependent on this existence of orientations and also on their choices up to a plus minus sign. And the existence in the setting that I talked about thus far, which was the projective setting, so compact, was proven by Gross-Joyce last year. And what I want to be talking about is really a generalization of this, where I take X to be a quasi-projective Calabi-Yau fourfold, meaning that I have the same setting as before, and I just relax the condition of the compactness. And this is a very rich family of Calabi-Yaus, kind of, so bunch of examples that one would want to consider are exactly non-compact. For example, toric Calabi-Yau fourfolds, they're very important in string theory. And the computations, the actual possible computations that one would imagine would be possible are exactly in this non-compact setting. So here one runs into the problem that these X groups do not make sense because the cohomology, so if one takes a vector bundle, then the cohomology of the corresponding resolution well, they do make sense, sorry, but they are infinite dimensional. So in particular, Serre duality does not make sense. So what one does is one restricts to thinking about compactly supported perfect complexes. So these are perfect complexes which are exact. So one should think kind of as having, if you had a two-term complex, then you would have that it is an isomorphism outside of some compact subvariety. So that's what one should think about, or one should think of. And for this, the duality again that I wrote down on the last page, on the last frame, actually does make sense. And what does one want to do with it? Again, there is another technical issue, and it is that the moduli spaces are non-compact, but one has an action. So because a toric Calabi-Yau fourfold has a natural action of a torus, one can use localization, and one gets these localization formulas which actually define the virtual fundamental classes. So this would be really a definition in that setting, even though it, like in the compact setting, this is an actual formula. Expressing the virtual fundamental class in terms of the fixed point locus of the action on the moduli space. But one has this additional factor, which is dividing by square root of the top Chern class of the normal virtual bundle. And the square root depends on a sign. So again, this is where the orientations come in, because what existence of a global orientation would say is that geometrically there is a particular sign up to a global minus sign that this would, up to which you could choose this. Oops, sorry. Yes, next slide. So let me talk about what, because I mentioned orientation multiple times now, but I haven't really said what it is. So let me talk about this. So let L into S be some complex line bundle over S being any topological space, stack, higher stack, anything, then if one has this isomorphism of L with its dual, then one can assign to it a square root Z2 bundle also associated with mu. And that's a Z2 bundle such that its sections are given by trivializations of L on U, such that the product of the two trivializations is equal to the adjoint of mu, meaning that the isomorphism from L squared into C induced by this, by bringing L star to the left. And and when Mx is the moduli stack of compactly supported perfect complexes, so something that classifies these as constructed by Toyen and Vacchier, one has a cotangent complex, which is a perfect complex. Again, one should think of it as a complex of vector bundles on this moduli space. And at a point, this complex has homologies given by the X groups. So one defines a line bundle by taking the determinant line bundle, which is an alternating product of determinants of these X groups. And one obtains, using Serre duality, which I described before, one obtains an isomorphism of this. Well, this is called a virtual canonical bundle on Mx. And there is an isomorphism of it with its dual. And the orientation bundle is exactly the square root Z2 bundle associated to this isomorphism. So this is a rather technical definition, but what does this mean? So before that, I said that one has this duality on the second X group. Well, here I'm really assuming now that I have, no, it works. Yeah, so one has this duality of the second X group, which choosing some metrics on these vector bundles in the complex gives you an actual isomorphism to the complex conjugate, and this gives you a real structure. So after that, if you choose a trivialization of the orientation bundle that I constructed before, then this trivialization corresponds to a choice of orientation of the real part of the second X group with respect to the real structure above. So like I said, this was already proven for the projective case, but my main goal was to prove this for the non-compact, and a more interesting goal was also to express this orientation in terms of some gauge theoretic orientation, which would allow to have more control over it, as I will explain now. So this is just a slide discussion to talk about some topological tools which make it easier to talk about the problem that I was working on. So if you have a topological space, and so if you have this triple of a topological space, a map from a point to X, and a summation map from X cross X into X, if these satisfy a monoid axioms up to homotopy, these are called H spaces. X would be called group-like if there is an inverse map from X into X, again satisfying group axioms. Then there is a notion of homotopy theoretic group completion, which is like in a setting of group, it would be a group completion from a monoid to a group. From F so such a map, which is a homotopy theoretic group completion, is a map from X into Y, such that it's not a definition, but one gets from it, in certain cases, a weak universal property, meaning that if you have a map into another group like H space, then there is a unique way that this fact. So if you have a map into some Z, let's say G from X into Z, then there is a map from Y into Z, such that the composition of these two is equal to the map G. And on these H spaces, one can define strong H principal Z2 bundles, which are pairs of Z2 bundles with this isomorphism Q, which is an isomorphism of the external product of O with itself into the pullback under the summation map, which is an isomorphism of Z2 bundles on X cross X. And this setting is exactly the setting that I'm working with. So on the category of perfect complexes, one has the obvious summation map, which corresponds to direct summing the perfect complexes, meaning kind of taking direct sums of vector bundles. And this map also comes with a natural isomorphism of the orientation bundles. So this turns the Z2 bundle, which I constructed before the orientation bundle, into, well, not a strong H principal Z2 bundle yet, but at least into a weak one, such that if it is trivializable, which is one of the conditions on it being strong, then it will become strong H principal Z2 bundle. So let me now talk a bit about how I'm going to prove, or how I proved this result. So I didn't talk even about what I want to prove. Oops. Sorry. Oh no, I said, so I want to prove that this bundle is trivializable, right? And oops. Okay, cool. Now, right, so let me present a bit of an idea of this proof. So, like I said, there are kind of these two parts of it. One of them is algebraic geometry, and one of them is differential geometry. On the algebraic geometry side, I had these compactly supported perfect complexes. On the differential geometric side, one should think of these almost as compactly supported pseudo-differential operators, in a sense that these are isomorphisms outside of some compact set.
Sorry, can you just repeat what differential complexes? I can't read this. Compactly supported what differential complexes?
Sorry, what do you mean?
The word I just didn't hear, and I can't read what it says. Perfect, compactly supported perfect differential complexes.
No, I said pseudo-differential operators.
Pseudo. Okay, thank you.
Pseudo-differential, yes. For a complex, one can take its determinant of the R home complex, which is really this alternating determinant. So the tensor product of alternating the tensor product of determinants of X groups, and corresponding to that, one has kind of the determinant of the pseudo-differential elliptic operator. And to Serre duality on this complex corresponds to the fact that on the pseudo-differential elliptic operator, one should have the kind of a real structure on it. So it should be expressed in terms of complexification of some real elliptic pseudo-differential operator. And the orientation bundle at a point corresponding to a perfect complex should correspond to orientation of the determinant line bundle, the real line bundle, or sorry, determinant line of this real pseudo-differential elliptic operator. So the issue with this kind of idea of making this connection is that it's hard to assign in a nice way to a complex this pseudo-differential elliptic operator. So instead, one should kind of let topology take care of this. And here, so on the algebraic side, one has the moduli space of perfect, of compactly supported perfect complexes, and it should correspond on a topology, on the differential geometry or topology side to compactly support K theory. This is the pointed mapping space from the one-point compactification into PU cross Z, and which is kind of the classifying space of K theory. And this is generated by complexes which are identified around this one point that you put at infinity in the one-point compactification. But there is no such equivalent notion of a one-point compactification in algebraic geometry. So for that, one has to do something different, and I'm going to talk about this now. So firstly, the vector bundles are replaced by algebraic vector bundles generated by global sections. The moduli space of this is denoted by T. And instead of a one-point compactification, one takes a smooth projective compactification with the additional assumption that the divisor sitting at infinity, codimension 1 subvariety, is strictly normal crossing. So it can be written as a union of smooth manifolds of complex codimension 1. Oops. Sorry. And then one can define this moduli, well, this is a moduli in scheme of vector bundles, of pairs of vector bundles identified on the divisor. And there is a natural map from this into the moduli stack of perfect complexes identified on the divisor. And inside of this sits our moduli stack, which is the moduli stack of compactly supported perfect complexes, by simply kind of pushing forward our compactly supported thing, and in the other copy having 0. Now the proposition, the whole idea behind this is that I can construct on this moduli stack a certain notion of orientation such that under this map it pulls back to the orientation that I want to, like, kind of pulls back to the Z2 bundle that I want to prove to be trivializable. So this is the statement of the proposition that there is something called extension data bow tie, for which there is a unique Z2 bundle on this moduli stack, O theta bow tie, and with a canonical isomorphism of its pullback with the orientation bundle on MX. So let me talk a bit about the construction of this, from which will also follow what this bow tie is. So if one takes the two perfect complexes identified by some quasi-isomorphism on the divisor at infinity, I will use for simplicity the notation that EF for determinant of the Arham complex between E and F. One has then the isomorphism induced by the Serre duality, but this time Serre duality also has this additional canonical bundle because it's not trivial because you compactify it. So you get an isomorphism of that E and that star FF to the dual of the first with this twist by the canonical bundle, and the dual of the second twisted by canonical bundle. Now the canonical bundle can be expressed as sum of the divisors at infinity, and this allows kind of to cancel this contribution which sits at infinity in steps, and I will explain how. So consider a line bundle L, then one has this standard short exact sequence from algebraic geometry, where SI is so this is a multiplication by the section of the line bundle associated to the divisor DI, and this is really the line bundle restricted to the divisor DI. And from using this and playing around with it, one simply gets that one can reduce this product of two determinants, one determinant of EE twisted by LDI and determinant star of FF twisted by LDI. And one can remove this contribution of twisted by the divisor from before. In particular, in finitely many steps, one can remove the entire canonical bundle by using the fact that it is expressed as this summation, obtaining an isomorphism, which is exactly the isomorphism of a line bundle with its dual. And as one gets this, one can assign square root Z2 bundle to this isomorphism, which I call the O theta bow tie, which is the orientation with respect to the bow tie data. And bow tie corresponds exactly, let me go back, bow tie corresponds to the choices of this section and order of the divisors that you have made as you go along. And in fact, like I said, the whole point is that the Z2 bundle pulls back to the orientation bundle on the moduli space that you actually care about. So instead of proving the orientability of this, I will now be proving orientability of this new Z2 bundle that I discussed. So let me state the main theorem. If X is a smooth Calabi-Yau fourfold, and I have such compactification with this strictly normal crossing divisor for any choice of extension data and the Z2 bundle constructed before. If I have this notation that CT is the mapping space from a topological space into BU cross Z, meaning that this is the topological space classifying K theory on T, there exists then a natural trivializable Z2 bundle on CX bar cross CD and CCX bar, so the fiber product of K theory. So this could be also seen as a K theory on X bar glued to another copy of X bar along the divisor at infinity. And there is a natural map from the product from this moduli space that I considered before, MX bar cross MD and CMX bar. I say here topological realization, so this is just the functor before that I discussed at the beginning, which maps algebraic things into topology. And there is such a functor, sorry, there's such a map into this K-theoretic space, such that the pullback of this K-theoretic or this K-theoretic bundle DCO on the K-theoretic space is naturally isomorphic to the new bundle that I constructed. Now, some immediate corollaries of these are that the map, so I had the inclusion zeta from MX into this product stack, and I had gamma, the map from the product stack into the K-theory space. And the composition of these is it factors through this space, which is really just something where 0 sits in the second component. And this space is really just a topological space classifying the compactly supported K theory on the non-compact Calabi-Yau fourfold. And the statement which follows immediately from the above result is that for a non-compact Calabi-Yau fourfold, the orientation bundle is trivializable. And moreover, we can say even more, and that is that the pullback of some orientation bundle on this moduli space, well, I wouldn't call it moduli space, on this topological space classifying compactly supported K theory, its pullback under the map gamma compactly supported to MX is naturally isomorphic to my orientation bundle. So similar argument can be also used to prove orientability of moduli spaces of stable pairs and Hilbert schemes, which is something that mostly people who do computations care about. So let me, sorry, how much time do we have?
Half an hour.
Yes, there are 30 minutes left.
Perfect. So let me sketch the idea now of the proof. So firstly, recall that I had this moduli space of pairs of vector bundles identified at infinity. And I had kind of this natural map which included, so vector bundles can be included into perfect complexes because perfect complexes are complexes of vector bundles. So there is a natural map from this stack, well, this is an in scheme, into this higher stack, which is the stack of perfect complexes on the compactification identified at infinity. And there is a map from these vector bundles into the moduli space of all, so just complex vector bundle on X bar viewed as a topological space identified at infinity. And this is the K-theoretic space that I consider, and knowing that K-theory is generated by vector bundles, there is also a similar way to map vector bundles into this K-theoretic space. So really, this is a mapping space into union of all BUNs, and this was BU cross Z, where BU is the co-limit of BUN. So in particular, that already tells you what the map from BUN into BU cross Z should be, and just composing with this map, one gets corresponding map here. And then one also gets this natural map gamma for free. And let me explain why. So all of the spaces that I have been talking about here are naturally H spaces. Here it simply corresponds to direct sum of algebraic vector bundles. Here it corresponds to direct sum of vector bundles, sum of K-theory, and here's sum of perfect complexes. Now, the bottom line on the bottom, I have group-like H spaces, which in particular tells me that if I have, by the universality property, if I have this map, which is omega composed with lambda, I do get a map from mx bar cross md and cmx bar into cx bar cross cd and cx bar for free. So this is how you get gamma. And additionally, because of this, I didn't mention this, but these are the homotopy theoretic group completion, this omega and delta. And because of them being universal and the classifying space of Z2, so every map into BZ2 is equivalent to a Z2, having a Z2 bundle. And because BZ2 is group-like, it's a group-like H space, then having Z2 bundles, so if I manage to prove that Z2 bundles, which are pullbacks of Z2 bundles here, are isomorphic in these topological spaces, by this universality property that I mentioned, and the fact that BZ2 is a group like H space, I obtain that the Z2 bundles sitting here on the bottom are also naturally isomorphic. So for this, I kind of need to construct some Z2 bundle here on the top. Let's call it DO into VX bar across PD and CVX bar. From this, so this vector bundle, this Z2 bundle will immediately give me a Z2 bundle on the bottom. And if I manage to prove that the pullback of it is isomorphic to the pullback of the orientation bundle, well, not the, but the bundle constructed with this extension data, then I will get the isomorphism of the Z2 bundle here on the bottom for free. So this is the idea. And now I would like to talk about the construction of the Z2 bundle DO. So for this, what I do first, so I will explain it actually on a picture. Easier, sorry. And oops, why does it not work? Okay. Right. So I have here my X, this non-compact Calabi-Yau fourfold, and I put this, so the divisor DNC is some codimension one thing, which kind of has this normal crossing, meaning that it intersects normally. The irreducible components, which are smooth manifolds, intersect normally. So these are the black circles. And what I do is I thicken kind of in a slightly more complicated way. One has to construct kind of tabular neighborhood of this normal crossing divisor to extend. So if we recall, we had these vector bundles which are identified on the divisor, and we extend where they are identified to this tabular neighborhood of the normal crossing divisor. And this gives me a map, if I go back to here, this gives me a map from VX bar across VD and CVX bar into VX bar, VT bar, where T bar is this is this tabular neighborhood. And then, sorry, excuse me. Then what I do is I construct submanifold of X with a boundary, such that the boundary lies inside of this tabular neighborhood that I just created. And I use So I construct a double of this manifold by gluing y along dy to itself. So I get, in fact, because my original manifold was Calabi-Yau, so in particular it was naturally spin, I get something which has a natural spin structure on one of the copies, and one can also get a kind of spin structure with opposite orientation on this other copy, and these glues together nicely. So one gets a manifold which is a spin manifold. And the map of vector bundles from this moduli space into, one can map it into moduli space of vector bundles, of pairs of vector bundles on this glued thing, is given by mapping the pair E and F identified using phi in this tabular neighborhood, by mapping it to E tilde F tilde identified using some phi tilde, where E tilde is E on this copy and E on the other copy, and F tilde is F on this copy and E on this copy, where here I glued using just simply identity, and here I glued using phi, and phi tilde is something which is identity on this new negatively oriented copy, and is phi in the intersection of y with the tabular neighborhood that I used to extend phi.
One question: Did you assume anything about the asymptotic behavior of your Calabi-Yau?
Well, this, not really, no. I don't think you have to, because I mean, the whole assumption is that you can compactify it by a normal crossing divisor, and you can do that always, right? So you can always the point is you can always put it into a projective. So yeah, so what I'm assuming is really only that it is kind of not a trivial Calabi-Yau where you just take an open subset of an already existing Calabi-Yau. That's something that I am assuming, because that's not very interesting. That would be covered by a compact case already.
Okay, okay. But then, so, okay, fair enough. That answers the question.
Right. So this is a map from the moduli space of vector bundles identified on this tabular neighborhood to maps, to vector pairs of vector bundles identified on this T tilde, which is the union of the negative copy together with the T bar intersected with Y. And now I can construct orientation on this moduli space. And for that, I will kind of use the standard way already used by Donaldson of doing this. So, all right. Yeah, so the map that I just constructed, I call it GY tilde. And as I said already, all maps are H spaces. So I construct the Z2 bundle by introducing this notion of topological stacks. So let me just very briefly mention what these are. So suppose you have, well, even for simplicity, let's say that you have a group acting on a topological space, group H acting on a topological space, then one can assign to it this topological stack X mod H, which, if you take a topological stack and a topological space and you quotient it out by an action of a group, you lose a lot of information because you kind of don't keep track of what the isotropy groups are of this action. But the topological stack plays the role of exactly keeping all the information of the isotropy groups. So in particular, kind of the groupoid of the action that you have is equivalent to such a topological stack. So these two informations are equivalent, and you can get one from the other. And this is exactly what I'm going to be using to construct my Z2 bundle. So I take, for two UN bundles on this glued spin manifold Y tilde, I use, I consider two such UN bundles. I identify them on T tilde, well, not identify, I assume that they are isomorphic on T tilde without assuming, kind of picking an isomorphism. And I consider the moduli, I consider the space of all connections on P and cross-connect all connections on Q, cross all the isomorphisms from P into Q on T tilde. So this is what this space means here. And there is an actual action of the gauge groups of P cross the gauge group on gauge group on Q on this topological space. So I get a topological stack by taking the associated quotient stack for this action. The action is obvious on AP and AQ, and here I just act by conjugation. Now the union of these stacks over all such pairs of UN bundles which are isomorphic on this T tilde gives me a new stack, and this is the stack which I want to construct orientation on, and you will see later on why this is the right stack to think about. So really, if you weren't thinking about this language of stacks, then this is also possible to think without that, and it's just you wouldn't get a very nicely behaved Z2 bundle and nicely behaved topological space. The point is that really, if you're not used to the language of topological stacks, you can think here of really taking a quotient by a group action. So now I have the, let me set just some notation. So if I have a real operator on a manifold, then its associated Z2 torsor or orientation torsor is defined by the orientation of the real line of real determinant line of the real differential operator. And then using this, so by setting this notation, well, I didn't really write it here like that, but by setting this notation, I can define the Z2 bundle on this moduli stack to be defined by saying that, so the Z2 bundle will be denoted by DO Y tilde and restricted to each pair of connections with an isomorphism, as discussed before. So this is a point of this, moduli stack, is given exactly by a product of the orientation torsors of the positive Dirac operators twisted by the connection of the joint bundle for the principal bundle P and Q. So maybe a bit more explanation here is necessary, and why this is the right orientation, because I'm kind of constructing orientation of something which lives on an entire new manifold. So why should this be really corresponding to something which tells me, gives me an orientation of things living on my original Calabi-Yau? So recall that we have a symbol map, which is a really continuous map from pseudo-differential operators of degree m into symbols of degree m. Using this notation, this twisted positive Dirac operator has a symbol given by a symbol of just the Dirac operator tensored with identity of the pullback on the pullback of the joint bundle to P, where pi is the projection from the tangent bundle into X. There is also a way of mapping, so reducing each elliptic. Right, so this is something again. I'm sorry, these slides aren't perfect for sure. So what I forgot to mention is that I obviously work with elliptic operators and elliptic symbols so that I can take determinants. So this is the notation that I'm going to be using for elliptic symbols of degree m. And there is a map from degree m elliptic symbols into degree 0 elliptic symbols. And the orientation only depends the orientation Z2 torsor only depends on the symbol of the differential operator, because, well, up to an isomorphism, and if you have and because the space of differential operators associated to a particular symbol is contractible, you can always construct natural isomorphisms. And in particular, one also have this well-behavedness of this orientation Z2 torsor under decreasing the degree of the symbol. So orientation of this degree 0 symbol is naturally isomorphic to the orientation Z2 torsor of the original symbol. So now, using what I discussed, one can using the formation of symbols and families, as already discussed, as already done in Donaldson and Kronheimer, and recently categorified by Appmeyer. One gets a Z2.
Sorry, I have a question. What is this map? There
Which
is a
one?
map.
Oh, you mean this one? Yeah. So this is essentially, you just take the. So if you have an operator P, you just take the square root of PP star.
Okay.
And you divide by it. So it's that's why you get a degree 0 thing.
Zero thing.
You do this this is equivalent thing to what you would be doing. Sorry, for the operator, you would be doing square root of 1 plus PP star. But for elliptic symbol, it really is just sigma divided by square root of sigma star.
Okay, thanks.
Yes. Right, and using kind of this deformation along a family, one can express the orientation at a point of two connections, nabla P, nabla Q, with an isomorphism of the principal bundle P and Q in T tilde as the orientation Z2 torsor associated to this pseudo-differential compactly supported elliptic operator. What I mean by compactly supported is because here this is a bump function chi, which is, if I go back maybe to this picture, chi would live inside of the original copy here. So in particular, everything outside of the original copy that the sections that this operator would be acting on would see. So this is not an operator, but an elliptic symbol, but let's not really distinguish between these. But everything that the sections would see under the action of this operator would be just this isomorphism. So in particular, the kernel and co-kernel of this operator would lie in my original Calabi-Yau. So this kind of explains why this is the right Z2 bundle to consider, because using this excision argument, this is what people call excision, one gets an orientation depending only on data inside of the original Calabi-Yau. Right. Yes. So let me move on from this to actually getting a Z2 bundle on this space, classifying vector bundles on Y tilde or pairs of vector bundles on Y tilde identified on T tilde. So I have this classifying space functor from topological stacks, which really one should think of as, like I drew before, kind of assigning to our topological stack a topological space such that there is almost no loss of information. And one can use the arguments from Arkadij Bojko and Donaldson and Kronheimer to show that the classifying space assigned to this topological space, the topological stack, which I defined on the previous slides, this union over all these pairs of principal UN bundles identified in T tilde. This classifying space is homotopy equivalent, even more so, it's naturally homotopy equivalent to this space Vy tilde cross Vt tilde Vy tilde. And using this, one immediately obtains a Z2 bundle do Y tilde on this space, this topological space, such that using results from Sauerkraut-Joyce, with some extra effort, one can show that this is a strong H principal Z2 bundle. Now let me actually go back to one of the things that I skipped. So here, notice I'm taking a dual over real line, which is not really something reasonable to do. It's almost like taking a dual of an orientation of a Z2 torsor, which doesn't do anything. However, one should really keep track of this, because if one takes a sum of two connections, then kind of the order of the determinants, if you take a dual, it interchanges. So and to interchange it back, there is kind of a very useful way of thinking about it, because these are determinants and one interchanges forms, so one gets an extra sign. And this is very important for the proof, because like I said, I had this notion of it being a strong H principal Z2 bundle, and if I didn't get this extra sign, it would still be a strong H principal Z2 bundle, but would be a wrong one, which one wouldn't be able to relate to the one that I have on algebraic geometric side. And even more so, one would get very nasty signs once one does computations. So this is actually a less technical detail, but for some reason I decided not to write about it. Right, and now we can define finally the orientation on this moduli space of vector bundles identified at the divisor at infinity by simply pulling back this vector bundle. To recall, we had this map discussed here. I pull back under this map this orientation bundle for y tilde. I pull it back to x bar, so this compactification by normal crossing divisor. And what I claim is that the resulting bundle, if I pull it back to algebraic vector bundles, is naturally isomorphic to the restriction of this algebraic geometric vector bundle constructed using extension data, restricted to algebraic vector bundles. So now this is something that I don't really want to talk about how to prove. This was probably just this very small detail I spent a few months on, and Hector knows because I was complaining to him about this for a while. So the rigorous proof, let me just kind of say 2 words about it so that I don't talk about it more. The rigorous proof relies on kind of developing a generalization of these excision principles for complex determinant line bundles, and kind of having natural up to a contractible choice of isotopies isomorphisms. And then one has to express this algebraic construction where I was restricting to something living on a codimension 1 submanifold. One has to express it using resolutions just purely in terms of vector bundles, and then just play around with these kind of one has to play around with the differential geometric side and with the algebraic geometric side to show that the real structure used to construct the Z2 bundles are there is a natural isotopy between them, which gives you an isomorphism of the Z2, a natural isomorphism of Z2 bundles. And then one can also check that this is really an isomorphism of strong H principal Z2 bundles. So let me now talk about something which is actually important for computations. And this is kind of the behavior of these orientations under direct sums. So the previous slide already proved, so by this isomorphism and knowing that the differential geometric Z2 bundle was trivializable, I managed to prove that my algebraic geometric Z2 bundle is trivializable. And it was an isomorphism of strong H principal Z2 bundle, which, if you recall, meant that they behaved nicely. There was an isomorphism between them under direct sums, or under kind of this summation map on the underlying H space. So the theorem that I have here is kind of summarizing this in a computation for people who want to do computations. And this is saying that if I have this compact, space classifying the compactly supported K, here it is, compactly supported K theory on X, and I pick alpha, some class in the compactly supported K theory, then I have for it corresponding connected component C compactly supported alpha, and I can restrict the Z2 bundle O compactly supported to this topological, to this connected component. Picking orientation on a connected components is unique up to a global sign, so that is why I'm doing this. So now if I have this summation map from BU cross Z into BU cross Z into BU cross Z, so BU cross Z times BU cross Z into BU cross Z, which is the natural obvious map, then by composition, I obtain a map from the compactly supported K, kind of a summation map on the compactly supported K theory space. And I also obtain this isomorphism tau compactly supported, which is an isomorphism of, which gives this O compactly supported Z2 bundle the structure of strong H principal Z2 bundle. And I also had already discussed that there is this isomorphism phi omega, which turns my orientation bundle into strong H principal Z2 bundle, now that it is trivializable. And the point is that if I restrict to product of these connected components, then one can compare two isomorphisms, this tau beta alpha and tau alpha beta, so corresponding to interchanging. So this is kind of a commutativity question. And I say that it isn't commutative, that I get this extra sign governed by compactly supported Euler form on the K theory. And what this tells me is if I do choose orientations for each connected component of this K theory space, then under this isomorphism, comparing these orientations under direct sums, I do get an extra sign. If I will get extra signs in front of kind of, because these are Z2 bundles which are isomorphic on a connected component. So in particular, two of their trivialization differ by a sign. So these are how these signs epsilon alpha beta are defined for each K theory classes alpha beta. And then these signs satisfy, based on what I said above, this relation expressed in terms of this compactly supported Euler form under interchanging the order of alpha and beta. And the point of having this isomorphism of strong H principal Z2 bundles is that if I do restrict, so if I restrict only to looking at perfect complexes corresponding to a K theory class alpha, compactly supported K theory class alpha, if I look at the corresponding topological space of these perfect complexes, and I restrict my orientation bundle, which is, as I said, trivializable, so there are two choices of orientation on this space, then pulling back the orientations from the K theory space gives me orientations. Sorry, this is not a connecting component. This is actually a very important part. This set actually falls apart into many subsets, and this is a kind of a big thing in algebraic geometry, understanding how many components there are and how these spaces behave. And what I'm saying is that I don't really care about, because everything that I care about is really just the K theoretic side of it, so I can take the union over all of it, and I get a natural orientation from the differential geometric side. And the pullback of the orientations satisfy the relations that the differential geometric orientation satisfied, namely that they differ by these signs given for K theory classes alpha beta, satisfying the relations, the commutativity relations I mentioned above. So this is where I'm going to end my talk.
Thank you very much for the talk, Arkadij. Yes, let's go back. All right, are there any questions?
I have a question.
Yes.
How does that relate at all to the moduli space of spin 7 instantons? And there,
Yes.
so what's the connection?
Right. So the moduli space of, well, kind of in the complex setting, let me go back to this. In the complex setting, your T tilde here would be empty, and your Y tilde would be just your original compact Calabi-Yau or spin 7 manifold. Well, these are not equivalent, but you know. And the spin 7 space, the spin 7 instanton moduli space would sit inside of this topological stack. Well, it would rather, this topological stack, you could restrict it to this topological space, and then it would be a bundle over this space. And the orientations that I deconstruct here, because of T tilde, well, in that case, they wouldn't be very interested, but if you just took just one of these terms here, then the corresponding orientation, so the Z2 bundle would be really the orientation bundle that you would care about on your spin 7 instanton space, because it would descend along the fibers of this topological stack, which would restrict to the topological space of spin 7 instantons.
Wait, so you say I can pull back my orientation from this moduli space of, like, say, stable bundles to an orientation of the moduli space of spin 7 instantons in the compact case?
What do you mean by this moduli space of stable bundles? Which space are you talking about?
I mean, you talked about the moduli space of some sheaves with a stability condition.
Ah, okay, that's what you mean. Yeah, so it's the other way, right? Because what I'm really saying is that you have your spin 7 instanton space, you have this bigger gauge theoretic space, which is kind of this topological stack of all the connections. And I say that the orientation on the stable or on the sheaves of these algebraic geometric sheaves is pulled back from the orientation on the gauge theory side. So in particular, like, for example, for the stability case, it's exactly the statement that you're saying, that like you look at just the vector bundles, and the orientation on the spin 7 instantons would pull back to the orientation on stable vector bundles and stable coherent sheaves in the algebraic geometric setting. So that's kind of sits inside of this argument, which is much more general.
Okay, and that's the compact case. And in the non-compact case?
Well, in the non-compact case, the orientation doesn't make sense, like I said, for vector bundles, unless you compactify like this. And in that case, you kind of, I mean, you're not really looking at spin 7 instantons anymore, right? Because you're looking at connections which are on this glued thing. So I didn't really think about it this way. I was just trying to prove something algebraic geometric.
Okay, no, the question doesn't really make sense. Yeah.
I mean, I talked about this actually with Hector before the talk, because I was saying that, like, maybe if you put some if you put some decay condition on the solutions, you wouldn't need to do this gluing of a second copy to have a compact thing over which it makes sense to take determinants and orientation bundles. And one could simply use this decay rate to have finite dimension of
Yes.
kernels and co-kernels, and maybe that would work. But that sounded like too technical thing for something that I wanted.
Mhm.